In a previous video, we have developed the formulas for compound interest, and those two formulas that we looked at in a previous video are these two. Okay. In this video, we are going to look at examples of the compound interest formula shown here, and we'll look at a couple examples of the continuously compounded interest formula here. Okay, so just a quick reminder, let me add a page below and we'll go ahead and get started. If we're using the compound interest formula, the amount of money, for example, in a bank account that has $0 in it, the initial amount of money invested, right? You multiply that by 1 plus r over n, and then you multiply that, raise that to the nt power. This is the compounded interest formula, where n is represents the number of compoundings per year, and r is given by the interest rate, the annual interest rate as a percentage, and t represents the variable time in years. Okay, so some examples we could do here is to just simply ask, imagine that you've gone to the bank. You're going to go to the bank with, say, maybe $200, right? You're going to give the bank that amount of money. The interest rate you're going to agree on with the bank is maybe, let's say, 20%, otherwise known as 0.2. You're also going to come to the agreement with a bank that maybe you're going to compound interest, that the bank is going to compound interest monthly or once per month, so 12 times a year, once a month, so 12 times a year for 1 year. And then we're going to wait some amount of time t, right? Let's wait on the clock, and let's wait for maybe 2 years before we get our money back. And the question is, how much money are you going to have, the amount in the bank after 2 years' time? Okay, this formula A is a function of t up here, so A would be a function of t. We know r, we know n, and we know time. So we know r, n, and t. We know a0, and therefore we can put these values in. A0 is $200, time is in years, n is equal to 12, and the interest rate is 20%, otherwise known as 0.2. Okay, this r over n value has a name. This is the variable I, so that would be 0.2 divided by 12, and this is the interest rate per period. In this case, the period is in months, so this is the interest rate per month, 0.2 divided by 12. So if we want to know how much we have at the end of 2 years, we would need to do 200 multiplied by 1 plus 0.2 over 12 to the 12 times, and time was in years, 2 years. So we needed to compute this quantity. Okay, that can be done in Desmos. I want you to see here that there's a couple different computations here. We have 200, that's easy to do. 200 is 200. Then we have this blue computation we need to come up with. Desmos, I'll come over here to our calculator. 1 plus 0, so it's 0.2 divided by 12. So that's 0.166. That's the interest rate per month. Okay, let's add that to 1. And now we can see our number in blue is 1.01666, repeating. Okay, and then we have to the 24th power. Okay, so let's handle the 24th power now. I'm going to leave the 200, and then we are going to do this number here. Order of operations says that we take the 1.0166, raise this to the 24th power, right? and we get 1.48. So 1.4869 stuff. Okay. Then we finally get to multiply and get our final answer, which is the amount in the account after 2 years' time. And this number should be bigger than 200. How much bigger than 200? 200 multiplied by this number. Okay. Oops. Sorry, I cut and paste wrong. Control C, Control V. There we are. So now we are going to have $297.30, maybe around 38 cents. Okay, and so this is kind of an approximation. I rounded that to a decimal. Okay, so that is how you use the compound interest formula. Okay, if we were going to answer the question, what is the most possible in the account? And this means for any number of compoundings in. Maybe the bank was going to be nice to us and compound. Maybe they were going to compound daily, or maybe they were going to compound 1,000,000 times a year. These are other options that could have been done. If we want to compound an infinite number of times, this is called compounding continuously. This is the most possible times that interest could have been compounded in infinity times or continuously. The way you would get the maximum amount in the account is to do the other compounding interest formula, the A0e to the RT power. And now we're going to use the exponential function, and the way we see the exponential function as a number A0, that's 200. And then we have the number e to the first, and then we're going to raise that to the RT power. This is the same thing as doing laws of exponents, right? Here, e to the 1 times RT is e to the 1 multiplied by RT. That's e to the RT. So what I'm saying here in this problem is that we can take the most that $1 can grow to, right, which is E dollars. So that's around $2.71. That's the most that $1 could grow to. And then we bring in our interest rate, 0.2, and then we bring in our time period of 2 years. And so what we can see here is that the maximum amount our $200 could have grown to would have been 2.71, or E dollars raised to the 0.2 times 2. Sorry, Desmos giving me a little trouble here. Times 2 with the decimals. Okay, so our most we could have had was about $298. And if I wrote the actual number E here, right, instead of 2.718, we would have gotten exactly equal to 200 e to the 0.4, which is 298, 200 times e to the 0.4. That's the $298.36. This is the most possible our money could have grown to. And so when we went from 365 compoundings per year to an infinite number, we only gained about $1, maybe about $1. Okay, which doesn't seem like a lot unless you're talking about millions of dollars that you start with A0. Okay. So there is a good example of how to use both of those formulas in the context in which they arise.